Continue where we left off with Xcode Instruments. The last place where we left off was pretty much determining execution frequency. Last time, working analyzing the main thread activity. So now we're at determining execution frequency. And again, anyone that's new, we're trying to learn Xcode instrumentals, and we're trying to do this so we can understand one, when a hanging is occurring within your app, how can we check for it, and basically how can we fix that. So a lot of the stuff to handle for performance for your actual iOS app. There's going to be a lot of reading theory and a lot of project work, but it's a really good skill to have, especially Xcode instrumentals. So you can learn how long a function might be lasting, if you have hangs in your app, what's causing them, and maybe where to go to fix them and identify them. So let's go. So right now where we left off, as I said, is determining execution frequency. And it says for this chapter is going to be learn about the 2 basic ways to fix hangs and how to decide which one to try. All right, so then a busy main thread hang is caused by too much work happening on the main thread. We know that based on our previous streams. If you're new to this, I highly recommend you at least check out the previous stream before. What I'm going to do is actually maximize this instead, so we're less distracted. It says a busy main thread is caused by too much work happening on the main thread. To fix it, you can do less work. You can do same work on a background thread, or you can combine the 2 approaches. So the first one is to fix it, you can do less work. You can do less work, and then it says, or you can do the same work on a background thread, or you can combine the 2 approaches. So it's either you do less work, which is whatever it might be hanging up the process, do less work, or you push some of that work to the background thread, or you do a combination of both. So you do some amount of less work, but also putting some of the work on the background thread. All right, so however, you'll need to decide which approach is more promising. So I guess it's based on whatever you need. So here you learn about the types of data you need to help you make that decision. So now, getting into it, so the overview. When you find a high CPU usage for a particular function, it's easy to jump to the conclusion that the given function is too slow and needs to be fixed. However, this isn't always the case. So last time in our stack trace, we were able to see that it was thumbnail view body getter that was taking up mad time. I guess that's why they're highlighting this, but based on what they just said, when you find a high CPU usage for a particular function, like we see this property being called or this function being called a lot, and it has a heavy weight, 4.5 seconds, they said it's easy to just jump to the conclusion that the given function is too slow and needs to be fixed. So that's what I would think too, but they're saying that's not always the case. And then, however, this isn't always true. The next portion is the reason for the high CPU usage may be that your app calls a given function too often. So it might not mean that we need to fix anything. It might be that we're calling it a lot of times. Maybe we have it in a for loop or something like that. And then it says, but that function itself runs sufficiently fast. So let's read this again. So it said the reason for the high CPU usage may be that your app calls a given function too often, but that function itself runs significantly fast. So the function might be running really fast, but it's being called so many times within your app. So then all of that pretty much just builds up. Okay, so it says it may be that the function indeed runs for a long time, and the best way to fix the hang is to move execution of the function to a background thread. So if the function is running for a long time, we could push it to a background thread. It may be that the function indeed runs for a long time, and the best. Okay, so there are 2 approaches. So we might have our approach where it's a function that runs really fast, but we're calling it a lot, and that could be an issue. Or the next issue could be that the function actually runs for, it takes a long time to run, and that might be a case where we want to push that process to a background thread. And then it says you need to know how often a function executes and how long each execution takes, so you can determine whether. So we want to know how long the function takes, so we can know if it's an actual function that process just takes a very long time, and how long each execution takes place, so you can determine whether to optimize the function itself or how it's called, or execution time is sufficiently long to make it worth the overhead of execution background. So we're trying to check, so let's read this one more time. So it said, you need to know how often a function executes, so how many times this function is being called, and how long each execution takes place. So you need to know how many times the function is getting called and how long does it take that actual function to run when it just runs one time. So to optimize the function itself, so we need to know this so that we can optimize the function itself, or how it's called, and also execution time is sufficiently long to make it worth the overhead of background. So when we know both of these things, like how many times the function executes and how long the function actually takes, we can optimize how the function is set up, and we can decide if we want to push some of that work to the background. So it said the article describes how to think about whether to do less work or to move work to the background. Because we can't make assumptions about execution frequency based on data from time profiler alone, you learn how to measure execution frequency and duration using instruments. So it looks like we're going to get introduced to a new instrument. We're not just going to be using time profiler anymore. So the first case that they mention is do less work. So for do less work, it says doing less work in this context means spending fewer CPU cycles. Because in our previous streams, we saw that so if I minimize this and we jump over to our instruments and this right here, and you can just ignore Xcode in the background for now. Actually, bigger. Yeah, so one thing we notice is that like inside our hang here, for our time profiler, which tells us what the CPU, how much process time that the CPU is working. So we see, if we scroll here, we see that a lot of these are pretty high. We have some that are 93, some that are even 113 or 125. And in the previous stream, they were saying that when it reaches 100, basically you've used up all of the core to perform this process. And then when the extra, you have to probably leak into another core. So we don't want it to exactly hitting, or we don't want our CPU to be hitting 100%, which is what it's doing when this hang occurs. It's actually going sometimes over 100 or pretty close to 100. So we're using up that entire core and maybe leading over to another core. So doing less work in this context means fewer CPU cycles. If the CPU needs fewer cycles to compute the desired result, then the work finishes faster. Okay. All right, so less cycles mean the work, less CPU cycles mean whatever function we're going to run, our process we're going to run is going to finish way faster. Let's maximize this again. Oh, okay. There are two ways to do this. To either do the same work more efficiently, or identify non-essential work and skip it completely. While you could go down the path of optimizing Xcode to use fewer cycles, using instructions more efficiently, or laying out memory, or finding other ways for the CPU to work, those options are often more work than necessary. Let's read that over again. All right, so while you could go down the path of optimizing the code to use fewer cycles, so we could try to change up our code so that we use fewer cycles. It says using instructions more frequently, efficiently, or laying out memory, or finding other ways for the CPU to do work. Those options are often more work than necessary. So we could do each of these things and it could end up being that we just do extra work. So yeah. So instead of fine-tuning low-level code to save a few percentage in execution time, first see whether your app is performing work that isn't essential to compute the result. So we're going to check, I guess, if our app is doing other stuff that like we don't really need it to be doing at that time or getting the result. And give us an example. So for example, if you're working on an email app and A decision you could make is whether you want your app to download all new messages from the server, which would be crazy since emails can have thousands of messages, or just the 10 most recent messages. If the person using an email app has thousands of messages in their inbox here, initially loading only the most recent can save a lot of time. Usually much more time than you could with more detailed CPU focused optimization. You're saying that instead of like, like when you have an email app, like in your mail app, instead of it fetching like 1,000, 50,000 emails, what we could do is fetch the most recent and like the most recent 10 or 20 or 30. And then when the user wants more, we could probably use like pagination. And then as they scroll, we just fetch more as they scroll. So we only fetch it kind of on demand. All right, so it's typically faster not to process an item than it is to speed up processing of each item. Okay, so now decide whether to look up or down the call stack. In analyzing main thread, which is the previous one on our previous streams, we did that. You found that the main thread spends most of its time running the body getter of the thumbnail view. There are two ways to do this work here. So before we continue, let's go back to instruments. And the part that they're talking is, so this is, remember, we're kind of focused on this area here where we have our hang. And in our previous stream, they kind of showed us how we could find out where is taking up potentially more time in the app. So right there, they tell us though, it says thumbnail view, but in the previous stream, they did too. So inside heaviest stack trace, we're just gonna scroll down here. So we're really gonna pay attention to the highlights in white or the default primary color, depending on which appearance you have. I'm using dark mode, so it's white. So if you're in light mode, it might be dark. I don't know. And then the gray ones, you can kind of just ignore those. Those are like stuff made by Apple that we need to run. And we're gonna look for another white coloring one here. And the one that we found was here, thumbnail view. So and you see how it takes 5.1 seconds. And if we scroll over a hang, you can see it's almost the same. So our hang is 5.91 seconds. So this is the area they're it's focusing on. And when we click it, it pretty much just pushes us to the view. So let's minimize that again. Maximize this again. And then we're gonna say in analyzing main thread activity, we found that the main thread spends most of its CPU time running the body getter of the thumbnail view. There are two ways to do this work here. So for that portion that I just showed you, so they're telling us the two ways how we can improve the work there. So we can call the body getter less often. So there are fewer body getter calls overall. Or we could look for ways to optimize each body getter. Maybe there is work each body getter performs that isn't necessary. So it sounds like the first thing that they're suggesting to fix issue where the thumbnail view is pretty much taking up all the time. The first one they said is call the body getter less often. So that's the first one, calling that view or for creating that view less often. Another option is look for ways to optimize each body getter. So go inside our actual SwiftUI view and see if we can make any updates in there. Because there may be work that each body getter is performing that isn't necessary. They're just assumptions for now, but it gives you an idea, like when you're probably looking at your app, when you're building something, you're like, you see a hang, you at least have some possible thoughts. It might not be the correct one right off the top of your head right away, but at least you have some possible thoughts for this. So now it says, if you determine that the body getter is scaled too frequently, is called too frequently, like we're calling it way too many times, look at what's calling the body getter and see if it's possible for the app to call it less often. So if you go with this approach right here, where it says it's calling the body getter a lot, what we could do is check to see if we could pretty much just call it less often. And then the next thing is, if all calls to the body getter are necessary, and you want to look at the work the body getter itself performs, you need to look at the function the body getter itself calls. So if we realize that basically we have to call the body getter, we have to call it this amount of times. Instead of doing that, let's look at the work that we're actually doing. So if we can't change the amount of times we're calling it, let's see if we can change the actual work it's doing and make that a little bit better. And if any of you have like a different idea of theory for what of explaining this stuff, feel free to just add it in the comments. It's just like we're pretty much just learning together, grasping Xcode instrumentals. So the next portion is, so we have the main thread here. We have some function, and it's called once, one function, and then it's called multiple times. Don't 100% get this image here. So we have a function that calls multiple times, and then for each function it's called one. Not 100%. So you need to know the number of executions because you need to decide whether your app calls a function often. So we want to know the number of times the app calls a function to see if it's too often. If your app calls it too often, you want to look at the callers of the function to avoid any unnecessary calls. If the function isn't called very often, you can either look at its callees and look for unnecessary work there, or you can look at moving the work to the function to the background thread. I feel like this is pretty much Apple re-explaining what they just told us, because it's basically just saying if we're calling the function too many times, let's see if we can reduce the amount of calls that we're making. And if we have to, or if basically we are calling it a lot of times but we need to make those calls, let's see if we can actually optimize the work being done, or maybe push some of that to a background thread, some of that work to a background thread, so it doesn't block or use up too much of the main thread. Next thing, so move work to a background thread. So this is one of the potential fixes. It says, as an alternative to doing less work, you may be able to change your app to execute same work in a background thread. Okay? Some work has to execute on the main thread. For example, anything that modifies the user interface must execute on the main thread. I'm gonna say this, you probably are watching this and you already know this, but any changes that you make to your UI, you have to do it on the main thread. That's not one of those that you can push to the background thread. Next, when you use Swift and SwiftUI, the corresponding functions and properties are usually annotated to run on the main actor. Okay, that's just making sure so when you use Swift and SwiftUI, corresponding functions and properties are usually annotated to run on the main actor. Basically, they're saying when you use Swift and SwiftUI, you basically have to run those functions on the main thread. All right, so, and because the compiler ensures that they execute on the main thread, they're always run on the main, and because the compiler ensures that they execute on the main actor, they're always run on the main thread. Okay, note, if you use Objective-C to access AppKit or UIKit, you may want to ensure your code runs on the main thread when it modifies the UI. Okay. Next, most work, however, doesn't need to execute on the main thread. But definitely UI changing work has to be done on the main thread. Consider a text editing app where you keep a running count of the number of emoji used in the current document. So if we have a text editing app and basically we have like some text view and we want to keep track a running count of the number of emojis in the current document, every time an emoji is added to that document, we just increment the number by 1. All right, so you can just imagine that app, I guess. Updating the number displayed by the counter needs to happen on the main thread. So for the app now, so remember it's like an app where so basically just picture a text editor, and every time or a user types in some text and then they type an emoji, we have to increment that count. But like they said here, updating the counter needs to happen on the main thread because we're gonna show this to the user using the UI. So, but counting the emoji in the text does not. So let's look at this again. So we have the app, we have a text editor app. It takes, the user can type in some text. Every time they type in an emoji, we increment it. But for actually counting the amount of emojis, we can actually push this to a background thread. This app can instead count the emoji asynchronously. So like we're saying, this app can count the emoji asynchronously in the background, and then once we get the number, we actually update the UI using the main thread. So we do those hard lifting for counting all the emojis in the text editor, and then for actually showing it back to the view, we have to push that to the main thread. We have to do that on the main thread. And then next section is avoid too much overhead of executing work in the background. While executing work in the background is often a good idea, it makes your code harder to understand, and there is some computational cost involved as well. It says if you have code like this, so let's see what we have. You have a function called updated display text. It takes in string, and then this new text here, we set it to a property in our class, self.text. Then for counting the emoji, which is this, do this. What would be good though is if we push this portion, actually counting the emoji, to our background thread. So we do that work on the background. And then for actually updating the emoji count, we could just do this on a main thread. Okay, so if you had code like this, you could make the emoji counting to the background using a detached task. So the kind of what I was thinking. So this is basically, so you can use tasks or you could use a dispatch queue.background thread. But honestly, everybody's been using tasks, so I'd say stick with tasks. So we could say tasks dot detached priority user initiated, and we could update it like that. Okay. All right. Alternatively, you could make the count emoji function asynchronous and non-isolated. Count emoji function asynchronous. Yeah, I like this. And non-isolated, which enables swift concurrency to execute it on the current thread pool. However, to call an asynchronous function, calling function must be asynchronous. Asynchronous as well. This is only possible because update display text in this example is also asynchronous, and we know that because right there for updated display text, it's marked with an async word here. All right, cool. So this is an asynchronous call, and because we're making an asynchronous call inside a different function, we have to also mark this function with async. So just to run this through, so this work here, which is actually counting the amount of emoji in the app, in the text editor, we're doing this asynchronously. So we're pushing this to the background thread. This work here where we're actually updating using the new count for the emojis that we got and updating the UI, we're doing that on the main thread. And we mark the main actor here, which ensures that this portion is run on the main thread. All right, however, to call an asynchronous function, the calling function must all right, so creating a task has a certain computational overhead in addition to the actual work that then runs in a background thread. So even suspending an existing task to execute part of it in the background, as in the second example using await, has a cost. Even though it's lower than creating a new task, similar considerations apply using dispatch queue with async. There's a cost, so I guess some drawback to using it like this. So let's see. So usually the additional overhead to achieve running work in the background is worth it. Okay, so it's worth it. So, but if the work item that your app runs in the background is small, it may not be worth additional overhead. So doing this work to actually push this to the background thread could be result in some amount of drawbacks. I wouldn't stress this too much unless you're doing huge, maybe you're handling like crazy size data set. Or in their example, say where we have some work that's done, but it's work that can return like really fast. It's not gonna take a long time. So for that case, we're saying it's not really worth pushing that to the background thread. So just like I said, but if the work item that your app runs is in the background is too small, it may not be worth doing additional overhead. And the time you save may be negligible or negative. So I guess you have to feel it out and kind of know when should you push certain tasks. So if it's a task that you know will take a lot of time, I would say push that to the background thread. If you know a task that's gonna be really quick, maybe capitalizing a string, and it's just one string is really small, I would say you can just do that. You don't have to push the background thread. So this code creates a new task for each individual character in the text. Okay. So each individual character in the text, we create a task. That seems like that's going to be very expensive computationally. So it has the advantage that all tasks can now run in parallel. Oh, we're running everything at the same time. Okay. Using all available CPUs on the device to process the characters. But running this likely requires more CPU time on the main thread than the original code, as the overhead to create a task is likely higher than the CPU time required to check whether a character is an emoji. Okay, so they're saying, so within this, so we have some text, and then we're looking through each character, each letter in the text, and we're creating a task for every single character in that text. So basically, if it's a long string, we're gonna create, if it's a word or string with 20 characters, we'll have created 20 tasks pretty much run this. And what they're saying here is this code creates a new task for each character in the text. It has the advantage that all tasks can run in parallel, with that part is good, using all available CPUs on device to whatever. But running this likely requires more CPU time on the main thread than original code, as the overhead to create tasks is likely higher than the CPU time. So because you're gonna have to be creating a task for every single character, you're saying that that's gonna be more CPU time on original thread, and the overhead to create the task is likely higher than create the task is likely higher than the CPU time required. So I guess you have to just feel it out and know exactly when's the best time to use this. Alright, so in general, don't dispatch or async a chunk of work if it takes less than 1 millisecond to execute. So if you have some work or process being done in your code and it takes less than 1 millisecond, you don't need to push that to the background thread. If it's taking more than 1 millisecond, you might want to push that to the background thread. All right, because remember, if we create too many tasks, this can actually end up hurting your CPU. So yeah. So you might have a case where your app completes a lot of 1 millisecond chunks that when added up causes a hang. If so, multiple chunks of work and dispatch. If so, combine multiple chunks of work and dispatch them together so you don't need to create a new task for each item. I guess it's grouping them. Okay, so one thing they mentioned here, it says you may, so even though they're saying if the task is less than 1 millisecond, you don't need to push that to the background thread. But you might have a case where your app computes a bunch of different less than 1 millisecond processes. And in that case, when you're running all of those, that can result in a hang. And that's when you might want to consider probably using a background thread. So remember, like, it can all be really small, but if you have a bunch of them, all of that adds up. All right, so to decide whether you want to move some of the work in the body getter to the background, you'll first need to know how long the runtime of a single body getter call is. So before we can, just like we said, we know if it takes more than 1 millisecond, then we push it to the background thread. So now for our thumbnail view, which is where we saw in our, not this one, let's open our instrument. We saw here and here. Now we need to find out how long is this actually taking, like how many milliseconds. Right here we see it says 5.01 seconds for the tutorial. I was gonna say, call it back. So it says if it gets less than 1 millisecond, focus on doing less work instead of moving each of the calls to the background. If it isn't possible, consider how to batch up the work of multiple body getters or executing a batch of work in the background. So I don't remember how you do this, but I think you can use like dispatch queue and like you can create like a work group item or something similar to that, and that's where you can put a bunch of tasks, smaller tasks inside it, so that they all execute together. But this is just me remembering off the top of my head. I'm still learning this with you. So the next thing it says is time profiler tells you the total CPU time the main thread spends on a method. Okay, so time profile, let's say that again. So time profile tells you the total CPU time, main total CPU time the main thread spends on a method. So we can use time profiler to find out how long the CPU spent on function, but not how many times it was executed or how long each execution took. So it can tell us how long. The time profile tells you the total CPU time the main thread spends. So we can find that out. With time profiler, we can find out the total CPU time the system spent on a function, but we can't find out the amount of times that function was executed. So say if we have a function that takes 5 seconds to complete, we can find that out with time profiler, but we can't find how many times. Like say if we call this 20 times, we can't find out that we called it 20 times. It says if you can find says if you can find out how many times a body getter executes, you can evaluate the average runtime. If you can find out how many times a body getter executes, you can calculate the average runtime from the total CPU time reported by the time profiler. All right. So like when you're finding the average and like you pretty much need to add all the numbers and then divide by the number of elements in the array to get the average. That's pretty much a similar thing. So say if we have a function that takes 5 seconds and we know it gets called 10 times, we would pretty much add those and then divide by 5 to get the average runtime from the total CPU time. Okay, we have to do this to really grasp this. So I'm still learning. I still need to grasp it some more, but I have a basic idea. So this is, but the main thing we just know is time profiler really just gives us the CPU time for each method. It can't tell us how many times to execute. Didn't know that. I thought it would. So yeah. So, but I'm sure they have an instrument that can tell us. So we might just need to keep reading. This is why knowing how often a function executes is important. Okay, so estimate the expected execute time and frequency. So I guess we're gonna find out now. So it says in general, the more executions of a function you see, the more likely it is that you can do less work by avoiding unnecessary computations. Okay, in general, more executions of a function you see, likely it is that you can do less work by avoiding unnecessary computation. So if we see a function being called mad times, they're saying it's more than likely that you can do less work by avoiding unnecessary computation. I want to see how they do this. So the fewer executions you see, the more likely that you can't easily do less work. Okay, so if we see we're calling it mad times and there's less than like we might actually need to call it that many times. If we're seeing it call less times, then oh, okay. Curious again. So in general, the more executions of a function you see, more likely it is that you can do less work by avoiding unnecessary computations. Okay. And then it says the fewer executions, if you see a little bit of executions, the more likely it is that you can't do easily less work. So it's gonna, if you're barely seeing it, the function being called, it's less likely that you can do less work. If it's being called many times, it's more than likely that you can do less work. So more execution calls, functions being called more, you can probably do some extra changes to kind of do less work. But if you see the function just barely being called a few times, less than likely that you can really change this around to do less calls. All right. However, you can easily move work to the background as each execution takes a longer time. What many and a few is depends on your app and the specification. You know your app best, yeah? For this sample app, you can estimate the expected number of executions for the body getter of the thumbnail view based on what you already know about the app. When you look at the project, you'll notice that the images, you'll notice that the images folder contains 129 image files. Let's see if we can look at image folder. You look at the project, you'll notice that the images folder contains 100 see more than 129 executions. At least one image. Before we do that, let's just look at the images. So did they put it in? So we have some images for city. We have some images for flowers. Doesn't look like 129 in here though, but it's a lot of images. All right, so let's jump back to instruments. And then it says, when you look at the project, blah, 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 you see 129 image files. And it says, if you see more than 129 executions, at least one image's thumbnail was computed twice, okay? Meaning that you could save this execution, storing and reusing previous results. So we have 129 images, so we should only be seeing pretty much just 129 calls to show this image. But if we're seeing more than that, then we know we're probably doing some extra work. Right, and it says, or at least one image's thumbnail was computed twice. And they're saying how we could, that means that we could save this execution by storing and reusing the previous result. Next, take a look at the collection view in the sample app in your iPhone and count the number of displayed thumbnails. Exact number depends on the screen size. On an iPhone 12 mini, iPhone mini, it looks like this. On an iPhone 12, like part of that. And then for iPhone 12, you see like 5 or 6. And then for iPhone 15, well, okay, so we see more because you know it's a bigger screen. An iPhone 12 mini, the app displays 30 thumbnails at least partially. On iPhone 12, it displays 33. So let's actually run our simulator because we haven't run that in a group and take a break from all this reading just to see actually some code. And we'll run this and we're gonna just look on our simulator to see how many images we see in a row, and then we're gonna get back to the read. So taking forever. Wants us to jump back to the reading right away. Okay, all right, so final loads, and as expected, so if you didn't see this before, when we click this is when we click this other tab, that's when we're gonna see the hang. I've seen it before, just expect like a 5-6 second wait after I click this. Eight seconds. All right, let's see how much we have in our row. And I'm using an iPhone 16 Pro Max. So I have 1, 3, partially of 7. So we see both 6 and a quarter. All right, so now let's jump back to our favorite part, the reading. So on iPhone 12 mini, the app displays 30 thumbnails, at least partially. 15 displays 33. 1 second. Charge my phone. Alright, so on iPhone 15 it displays 33. Each thumbnail is backed by a thumbnail view. When you measure the execution of its body web getter, you'd expect to find about 30 to 33 executions, depending on the screen size. If you see significantly more than 33 executions, some of those are likely unnecessary, as there are needs to render the initial screen. That makes sense. So if you're 30 thumbnail views, you'd expect 30 executions, but it says expect to find about 30 or 33 executions depending on the screen size. Makes sense. If you have 30 images, you're expecting that amount of execution. If you see significantly more than 33 executions, so if we're only showing 33, if we only have 33 images supposedly showing, and we see more than 30 to 33 executions, some of those are likely unnecessary as they aren't needed to render the initials. So basically, maybe we're showing images that aren't even present on the screen visually for the user yet, like they may be off screen, and we're loading them. And really, we just need to load whatever we're going to show as the user arrives. So the first 30 to 33. Then it says they may be needed later when a person using the app scrolls them into view, but this never happens. But if this never happens, the computation was necessary. So they were loading more images. So we're loading the entire 120, but the screen can only show 30 of those images. But we find out that we're actually executing for 120. So that's extra work that we did for images that we're not even, the user isn't even seeing, and that might be helping to cause the hang. This is just me off reading. Let's just see how it goes. The next thing it says number of thumbnails. They give us a nice little visual, and they said this portion, say from 0 to 35, is required, and then they say maybe this portion here may be needed. And then anything past that, they say is definitely unnecessary. All right. So similarly, you can use a number of executions to estimate the average execution duration to judge whether moving the execution to the background is worth it. Because remember, we said if an execution takes less than 1 millisecond, more than likely you don't need to push that to the background. But if it's a group of those small millisecond operations, they can add up. So next, from your investigation in the previous tutorial, go watch a previous stream, you already know that the total CPU time on the main thread is about 4.5 seconds. And this is Apple's time. Our time was a bit different. It was around 6 seconds. And as you just saw, it was like 8 when I just ran the simulator. So it all comes down to kind of the MacBook, the machine you're using. All right, for the body getter. If you were to find about 500 executions, that would mean the average execution time is about 9 milliseconds, which is horrible. That's long enough for you to consider moving the work to the background. Okay. All right. So, however, if you found that the body getter had 5,000 or more executions, average execution time for each one would be about 1 millisecond. It's too short to efficiently execute in the background. But 5,000 execution is far too many for this sample app based on estimates above. Yeah, when they say that 5,000, I was just like, why would it even be close to 5,000? But they're just giving us like an example of, yo, if you see this, and especially for this app where we only have 120 images, you know something's wrong. The next it says, while moving work to the background, 5,000 executions, it's likely not feasible. In the scenario, there is a lot of potential to do less work. All right. It says because the app only displays a little more than 30 images initially, anything more than that has the potential of optimization. Anything more than that has the potential for optimization by not computing these additional thumbnails or doing so later. If you have less than 500 executions, that means each individual execution takes about 10 milliseconds, which is long enough for you to move that to the background. Let's read that again. So because the app only displays a little more than 30 images initially, so it only displays 30 images initially, anything more than that has the potential for optimization. So if we only have 30 images and we're seeing more executions than 30, way more, we should look into some form of optimization by not computing these additional thumbnails or doing so later. Okay, so if you have less than 500 executions, that means each individual execution takes about 10 milliseconds, which is long enough for you to move that to the background. Okay, cool. And they give us a nice little chart here. For this, you can make the following plan for the sample app. If there are fewer than 40 body executions, it isn't worth trying to do less work. Look for ways to do the work in the background thread. Okay. If there are more than 500 body executions, the most promising path is to look for ways to reduce it. Okay. If there are between 40 and 500 body executions, you can choose whether doing less work or moving work to the background thread seems easier. It may very well be worth to do both. So you can do pushing it to the background, pushing some of the work to the background, which they say here. If there are fewer than 40 body executions, we could push some of the work to the background. And then if it's more than 500 execution, we could look for ways to reduce this number. So we might need to do some work for the actual process. Might need to make some changes for the actual process. And then if it's in between 40 and 500, we could work on doing a combination of pushing some work to the background thread and also doing some optimization to the actual function. So now, here where it mentions determine how often a function executes, which is pretty much the goal that we were looking for here. So it says, as you've seen above, it's essential to know how often a CPU usage function executes, so how often the function gets called. Ideally, you would also gather data, how long each individual function call takes. So we should be able to get that from time profiler for how long the call took, but we won't be able to find how many times the function was executed. So then there are various ways to do that, but time profiler alone can provide this information. We know this, they told us this earlier in the pretty much the reading. It says time profiler works by sampling each CPU on the system in regular intervals. For each CPU, it records which thread and process are executing on the CPU and what's the current call stack for that thread is at the point of sampling. The default sampling frequency is 1 millisecond. I guess the time profiler checks like every couple intervals, right? 1 millisecond intervals. It makes these checks to check how it's handled, how the system's handling it. When targeting a single process, Instruments filters out all samples that don't belong to the current process. When selecting a single stack track, a single track thread, Instruments only uses the samples for the specific thread. So to look at the tracks are pretty much, let's open up Instruments again. So each of these are different tracks. So we have a track for time profiler, we have a track for point of interest, thermal state, hangs, which is here, and then the processes, and then the main thread right there. Let's jump back to the reading again. And it says it then aggregates the samples. Go back here first. So when targeting a single process, Instruments filters out all samples that don't belong to the current process. So if we click on that in Instruments, we can do that. When selecting a single track thread, Instrument only uses the samples for this specific thread. Okay. It then aggregates the samples that match the current filter in the profile detail view. However, time profiler doesn't collect any information that would allow it to determine whether the same call stack seen in two different samples belongs to the same call of a method or two different calls of the same method. You can find the individual samples by switching to the samples view. Yeah, we're going to read it again. So it says, it then aggregates the samples that match the current filter in the profile detail view. Okay, so if we open up Instruments, scroll down back here. All right, it then aggregates the samples that match the current filter in the profile detail view. And this is our profile detail view, and that match the current filter in the profile detail view. I'm focusing here, so this is our time filter, and I believe this is our profile detail view. So it's showing these that take 5.13 milliseconds. or 5.13 seconds, and it says, however, time profiler doesn't collect any information that would allow it to determine whether the same call stack seen in two different samples belongs to the same call of a method or two different calls of the same method. I don't completely get that right there, but let's keep reading. So it says you can find the individual samples by switching to the samples view in the detail area, selecting a track with a CPU usage. I wish they had like the play button here right now that we could see this. I think, oh, so we can click down on this and let's sample. Oh, so we can see a different view. So we have a profile view and we have a sample. Let's switch to samples again. And it says, however, time profile doesn't collect any information that would allow it to determine whether the same call stack seen in two different samples belongs to the same call of a method or two different calls to the same method. You can find individual samples by switching to samples view, the detail area, after selecting a track with selecting a track usage. Okay. Previous illustration shows a simplified example of functions a thread might execute. Below you see how time profilers call tree view and heaviest stack tree view aggregate the collected samples. The previous illustration shows a simplified example of the functions a thread might execute. Okay. Below you see how time profilers call tree view. Let's switch back to our profile there. Below you see how time profilers call tree view and heaviest stack trace, which is over here, to aggregate the collected samples. So we have something called, so let's look at it. So these are pretty much, they're not the same, but it's like pretty much the same information. Heaviest stack trace will like highlight the next heaviest function that took the most time and just keep catching those. And then the call tree pretty much shows like the entire procedure. So let's see if this makes sense. So we have a start, have it for the call tree start is 9 milliseconds in wait. The same thing over here in heaviest stack tree. For text change, we see that it's 6 milliseconds. The same 6 milliseconds here. Count emoji 4 milliseconds, but we see that there is a self wait of 2 milliseconds. Let's find out what that is. I think we're gonna learn that more here. And then for is emoji, we have 2 milliseconds here for self wait, but it also has a wait of 2 milliseconds. Let's see how they work with this. So there are a few things to note here. As the profile view filters to just the main thread of the target process, it doesn't count for all the work on the system. Okay? It filters out CPU time that other processes and threads spend. Okay? That's desired when looking at hang analysis, as you want to focus on the main thread of the target app. I wish they had a visual of like a GIF like how they have before GIF or whatever. There is no differentiation between the number of executions and the duration. The profile view attributes 2 milliseconds of CPU time to both collection view and row. 2 milliseconds CPU time to both collection view and row. So this is this right here, this view and row. Even though the single execution of collection view took about 2 milliseconds. Okay, so let's read again. So it says the profile view attributes milliseconds of CPU time to both collection view and row, even though the single execution of collection, here, so scroll up, it says even though the single execution of collection view 2 milliseconds, but there were 2 executions in a row. A row got executed, each of which took 1 second. There is no way to differentiate between the 2 execution patterns, as time profiler only often saw a specific one. That was alright. So okay, so we'll have to read it over again, but there are limitations to time profiler's accuracy. For example, the set text method, which took a little less than 1 millisecond. Let's look at set text. Might be inside our heavy stack trace. Scroll down. See right there. There are limitations to time profiler accuracy. For example, the set text method took a little less than 1 millisecond. Doesn't show up in the call tree as it happens with samples. Similarly, so it's not supposed to show up here. Similarly, for example, the set text method. For example, set text method, which took a little less than 1 millisecond, doesn't show up in the call tree as it happens between 2 samples. Similarly, the sampling only hits 2. It's 2 of 5 is emoji executions. 2 of 5 is emoji execution. These differences even out with higher sampling counts. And then it says the call tree view also translates as where are we? So it says the call tree view also translates sampling counts to duration by multiplying the length of a sampling interval by the number of samples for each symbol. It attributes a 2 millisecond duration to is emoji. As there were 2 samples and the sampling frequency was 1 sample per millisecond. In reality, total time spent by all is emoji execution was closer to 3 milliseconds, and each individual execution only 0.5 milliseconds. The same is true for the heaviest stack trace view. The call tree in Instruments also has a column for number of samples. It is hidden by default, but you can show it. Still, the number of samples for a given function doesn't allow any interferences about the number of execution. A sample count of 2 for is emoji is in the call tree. A sample count of 2 for is emoji in the call tree doesn't mean that it executed twice. Okay? So if we see a sample count of 2, that doesn't mean that it executed twice. Instead, it means that only 2 of the samples back traces contain is emoji. In reality, it executed 5 times. So it says, instead it means only 2 of the samples. So if we see a sample count of 2, it doesn't mean that it only executed twice. Instead, it means only 2 of the samples back traces contained in emoji, is emoji. So it's all based on whatever is in our back traces. So due to the way time profiler collects data, I can't tell you how often a function executes or how long it ran. It's the profile view and the heaviest stack trace view further summarize the data. Due to the way time profiler collects data, highlight this, can't tell you how often a function executes or how long it ran. Profile view and the heaviest stack trace view further summarize the data. I thought time profiler could at least tell us how long it ran. It couldn't tell it. I know we can't tell us how many times it executed, but I thought it could at least tell us how long it ran. I guess not. Important. Always remember that the duration displayed in the profile views call tree isn't the time for a single execution of the given function, but instead the sum of all execution times, all executions of this function. Oh, okay. So if we're calling it like multiple times, it's not just for the one time it's called, it's for all the time that it's called. Okay. So use specialized instruments. Depending on the specific domain, there may be specialized instruments that can already measure the exact behavior of your app that you're interested in. In the next tutorial in this chapter, read reducing main thread work by doing less. You can use SwiftUI View Body instrument. Oh, so there's an instrument called SwiftUI View Body. We can definitely gotta check that out. To trace the individual execution of a view's body getter. Other examples of instruments that measure individual execution specific part of your app are the HTTP traffic instrument, never use that, and the Swift task, never use it either, but we'll learn it. And then it says, however, you may need to occasionally add your own instrumentation, logging a signpost to the points of interest category allows you to see these events in the points of interest track and track in instruments, and is a good way to count how many there are. So let's read it again. So, however, you may need to occasionally add your own instrumentation. It says logging a signpost to the points of interest category allows you to see these events in the points of track in instruments, and is a good way to count how many executes there are. So we should use points of interest for that. If we minimize this and jump back to instruments, we do have a track called points of interest. But we honestly haven't used this yet, so maybe in the next tutorial we will end up doing that. Okay. The WWDC 2019 session, Getting Started with Instruments, describes how to use signposts and the points of interest instrument to measure individual function executions. So yeah, we have to use that points of interest instrument. Or additionally, see recording performance data for more details on how to capture performance data using signposts. So in the next portion, we will be looking at reducing the main thread work by doing less. And this is going to focus on, this tutorial uses a SwiftUI View Body instrument. Never heard of this one, so this is going to be really good. And most apps use SwiftUI now, so this will be good for pretty much anybody. So using the SwiftUI View Body instrument, analyze the body getter execution of SwiftUI views. So we'll be able to analyze that. And then it says, after confirming that there are too many instances of a specific view, you'll use lazy evaluation, only do as much work as necessary to reduce the total amount of work performed. So let's read this again. So we're going to be using an instrument called SwiftUI View Body, and that's going to help us to analyze the body getter execution of the view, SwiftUI view. And then after confirming that there are too many instances of a specific view, like we keep creating them, these views many times, we will use lazy evaluation to only do as much work as necessary to reduce the total amount of work performed. All right, so that will be inside the next stream, and that's going to focus on, like we mentioned, using the SwiftUI View Body instrument. So if you like this, just like, follow, and subscribe. And yeah, just leave your comments on like anything that you want to discuss more about. And yeah, we'll continue from there.